I'm going to start talking. So how's everybody doing today? That good? All right, so we had a homework due today, and we're going to continue talking about stellar interiors. I haven't graded the homework yet, so one of you asked, hey, I got a little bit of an extension to redo the problems last time. I haven't graded them yet. If you can get them in before, like, I'm going to start at like 8:15 tomorrow. So if you can get them done by the end of the day, if you want to redo a problem, I haven't looked at them yet. So free extension. Don't bank on those because sometimes I'm actually on top of my shit and get the stuff graded. But today, if you want a little bit of an extension, I'm going to go over them. Yeah. Does anybody have any questions on anything? There was a reading up that we're not going to get to today. So, well, we're going to start some of the reading today. So, okay, so let's do the first one. So, did you guys find the diameter of Keck?
Yeah.
What did you find?
Clear.
Yeah. I realized
Like 10 meters.
it's 10 meters. Yeah, I realized that I say find sometimes when I mean like actually compute. There I just meant like go look it up. Okay, so Keck is 10 meters. What'd you get for for your resolution in arc seconds?
1.6432 times 10 to the negative 4.
That's too many. That's too many in the exponent.
I got .0.
Should only be 2 in the exponent.
Oh, cool.
You should get like 0.01.
Yeah.
Right?
Were we supposed to like convert to radians?
No, I wanted you to convert. You get it in radians. You got to convert to degrees. So.
Instructions unclear.
The formula that was in the notes
Oh, no,
gives you the thing in
instructions
radians,
unclear.
and
Yeah.
then you like multiply it by something to get arc secs.
Yeah, so theta is 1.22
Yeah.
lambda over d.
Okay.
You guys getting there? I don't know, everybody's talking amongst themselves. Did you guys need to just talk for a second? That's all right. Like, no, I don't mind. I don't mind collaboration. I just don't want to derail useful conversation.
No.
So okay.
That's the number you multiply.
Lambda is,
Yeah,
so theta
I have
is
that.
lambda over d. You guys are still stuck. Oh, sorry. No worries. I mean, if you're talking about this, we can make a.
We're talking about part C, but we'll just wait, and you'll get there.
Okay, cool. Yeah. So we'll get to the details of C in a second because I realized I just worded that question right. I just worded the question, but I didn't word it carefully enough. I should have made that a factor of 100, not a factor of 10, because as it's worded, it's a little confusing. So I'll talk about that in a second. This gives you the answer in radians. So you plug in 657, is that what I said? Nanometers divided by 10 meters. I'm just going to assume that you guys can all work with units at this point. And you get a number that was like 8 times 10 to the minus 8 radians, right?
Yep.
And then you got to convert to arc seconds. So how do I convert to arc seconds?
Times 206,264.
206. What was the rest of it? 0.
264.
Right. This is the number of astronomical units in a parsec. Or the number of arc seconds in a radian. How do I get this number? What's in it?
2 pi.
So it's 2 pi.
60 degrees.
So how many? Let me just work through how you get it. So how many degrees are in a circle?
360.
How many radians are in a circle?
2 pi.
2 pi.
So 1 radian is 2 pi over 360 degrees. No, sorry. 1 equals 2 pi radians over 360 degrees. How many arc seconds are in a degree?
3,600.
3,600, because it's 60 times 60 minutes and seconds, just like seconds in an hour, which at this point, I hope everybody knows that there's 3,600 seconds in an hour. You should have done that like a million times by now. Same thing, 3,600 degrees in a second. So it's 2 pi over 360 times 3,600. That gives you this. No, 360 over 2 pi gives you times 3,600 gives you this. So you multiply this by this, and you get something like 0.01 arc seconds. Cool? So, okay. And then for the second one, what'd you get in arc seconds?
6.847.
You got like 6. I got like 6. So what'd you use for the diameter of your
I got 28. I don't know, I searched it up.
28 arc seconds?
28 millimeters for the foam lens diameter.
Okay.
Yeah.
I used 2 millimeters because that's what it looked like to me.
Yeah, that's what I used.
And so you should get a comparably small resolution. Let's see, for the last one.
2 millimeters.
So for the last question, so let's see, I got 16 arc seconds for my phone. I used 2 millimeters.
I got something times 10 to the negative 12
In radians?
in arc second. No,
I'm gonna say you got to divide instead of a multiply somewhere in there.
I use like 26 millimeters because I looked it up. I didn't actually measure it.
Yeah, how
Yeah.
big is 26 millimeters? That's like an inch. So there's 24 millimeters in an inch.
Yeah,
So
no,
these
I
are not
divided
really
it.
that big, but close enough. I don't really care all that much.
You're
If
supposed to
I
multiply
want a
and
specific
divide.
number, I'll feed it to you.
Yeah, I looked it up
Yeah.
and it said the iPhone is.
It's,
24
this
millimeters.
formula.
Oh, I actually meant
Times
The focal length or the diameter?
The diameter.
It's 24 millimeters?
That's what it
Yeah,
said.
it would make sense. This is about 26. Like this distance is about 26.
Yeah.
That would make sense.
The aperture,
The actual-
aperture
the
size
actual-
is not 26 millimeters.
Yeah.
It's like 2 millimeters.
Which is why I was
millimeter. 26 millimeters is like my thumb.
Yeah,
So
that doesn't make sense.
So that's a
now I
little
think
big.
about it,
I'm
but-
not gonna ding anybody about that, but think about the numbers.
What about something like 6?
Yeah, so we all got comparable numbers. The last one, I asked to compute the angular resolution of JWST and Hubble. And so I get, when I did it, I got that the HST range from 0.01 to 0.03 millarc arc seconds. And then for James Webb, I get 0.02 to 1.08. So, okay, this number is a lot bigger than this number. This number is a lot bigger than this number. But this number is about the same size as all of these numbers. So the high resolution end of JWST is the same as Hubble.
But I feel like if you divide
So,
it, then you get something.
Two of
negative
first
12.
approximation, Hubble and James Webb have about the same
No, I
resolution.
multiplied it. This was-
You doing all right?
I know that I'm doing the exact same thing as she is, but I'm getting
Maybe it's a calculator.
completely different
So I
things.
feel like if you divide.
That's a details question that we should worry about after class. You
Okay.
don't get sucked into those weeds right now because
Okay.
you'll lose the meat of the rest of it. So it's just you got a calculator problem. I wouldn't worry too much about it right now. Okay, so everybody good with the first one? We'll move on to the second one, where we actually do stuff. So this is the one that I think everybody had trouble with. So show that for my 2 stars. So I've got 2 stars orbiting each other. Each one traces out an ellipse with a semi-major axis of A1 or A2, and the reduced system traces out an ellipse with semi-major axis A. So now we want to show that A1 and A2 equals, the sum of A1 and A2 is A.
Could you show what like a reduced system? I
Yeah.
haven't been able to wrap my head around what a reduced system looks like. Just one ellipse. Is it 2 masses on one ellipse, or is it one reduced mass on one ellipse? Yeah,
Yeah, so, because we do all this math and we have these nice equations, but then what we've done is we've taken something, okay, I'm going to draw this very carefully. So I've got an ellipse, I got a focus here and a focus here. This is my first ellipse. Oh, do I have colored chalk? That would be so handy. Sometimes there's colored chalk, but I think I ate it all.
Susie Delta would be like,
It's just a shadow.
You needed some pepper.
Okay, so you gotta use your imaginations.
we need to get some more chalk for this room.
I'm gonna put this one over here. So this ellipse looks like this. And this ellipse looks like this. And my objects are going to be in opposite phases of the ellipse at the same time. So they'll both be at perihelion at the same time. So we'll call this 1 and this 2. sorry, that doesn't make any sense. Let's call this circle 1, and this one is 2. So this planet is 2, this is planet 1, this is planet 2, here's planet 1 again. So they're going to orbit like this. And they're both going to trace out ellipses. And what we did at the beginning of the semester, all of that math was about the bar joining the two ellipses. So if you think about this bar, it's going to get bigger as they're over there, and then smaller. This is r, and that's what we did all that math for. So we have r equals a times 1 minus e squared over 1 plus e cosine theta. This is true for an ellipse. That's what an ellipse is. So r is the difference between these two things, and it traces out an ellipse as these things go like this. These things also individually trace out ellipses as they move around their orbits. The center of mass is at this focus. Is at one of the focuses. So we can treat this problem as two bodies orbiting the center of mass, or one object with a reduced mass orbiting the total mass at a fixed radius. It works out to be the same math, but going backwards is hard. So we did all this math. We also know that r, here I'm going to write these over here. So let's see, r equals a 1 minus e squared over 1 plus e cosine theta. We also have r1 equals a1 1 minus e1 squared over 1 plus e1 cosine theta. And then r2 equals a2 1 minus e2 squared over 1 plus e2 cosine theta. Okay. Is everybody good with that so far? With the geometry? Does the geometry feel like it sits a little bit in your stomach? Because that's the hard part 1 is drawing the right picture. Hard part 2 is remembering that this is a signed quantity. So if I'm looking at this, I'm going to have R1 here and R2 here. The difference is the sum of the distances from the focus. So there's a sign that threw me off when I was doing the problem. Yeah.
Why does the sign, the negative sign matter there? If this is a radial coordinate system, wouldn't the sign of r just indicate like it goes in the opposite direction? But all of our r's are the same. We're just changing angle, right?
Yeah.
So the sign will only depend on the angle, right?
Yeah. The sign, one of them's got to be negative. So r equals r1 minus r2, right? But if I think about, so everything's measured relative to here, r1 goes like this and r2 goes like this. R is this plus this, right? Or this minus this, but they're pointing in opposite directions.
Oh, is that what that minus sign means?
Yeah, because if r was at apohelion instead of perihelion, it would be r2 minus r1, even the way you've drawn it.
Yeah.
Right?
It's always r2 minus r1. I wrote it r1 minus r2. Just do it r2 minus r1 because that makes more sense. The math works out regardless of which way you write it.
As long as one's.
But so this is my origin. R1 is here. R2 is here. R is R2 minus R1, which goes this way. Does that make sense? So when you're writing down and doing the math, there's a minus sign that you've got to be careful about. And I'll show you where the minus sign shows up in a second. So let's not worry too much about it for now. So let's set things up a little bit more.
Would it be true to write r is equal to the magnitude of r2 plus the magnitude of r1?
No. Maybe. I can't do the whole derivation in my head, so I'd be careful about that.
Okay.
So let's talk about an apohelion. An apohelion, theta equals what?
0.
0. because the theta is always relative to aphelion from the semi-major axis. So theta is 0, so we can say, actually I'm going to write this, I'm going to trim this and do a little bit, so at aphelion theta equals 0, so we plug theta equals 0 into here and we get r at aphelion, we're just going to call it r, equals a1 times 1 minus e1 squared, nope, a times 1 is e squared over 1 plus e. Cosine theta is 1, because theta is 0. This algebra I can do, this is equal to 1 minus e squared, 1 plus e squared. So let's write this over here. 1 minus e squared equals, I just said that totally wrong, 1 plus e, 1 minus e, right? This is going to be useful in a second. This 1 plus e cancels that 1 plus e, so r equals just this simple 1 minus e, because the plus terms cancel. Pretty good. I also have r1 equals a1, 1 minus e1 over, nope, over anything, and r2 equals a2, 1 minus e2. R equals r1 minus r2, and here's where you have to be careful with the minus sign, because you think about the origin. R1 is in this direction, R2 is in the opposite direction. So thinking about it as the sum of the absolute values is probably okay, but I think that any time you have an absolute value and you try to do math, things are going to get hard. So it's better to just leave it as a minus and take care of the sign by hand. So then we're left with, we'll just plug in these three things. A times 1 minus e equals a1 times 1 minus e1. This turns into a plus because they're in opposite directions. a2, 1 minus e2. And then at aphelion, sorry. I wrote the wrong thing. At perihelion is theta equals 0. At aphelion, we're left with, let's do this over here. Sorry, my board's cute. We have theta equals pi, so r equals a times 1 plus e from the same object. So the cosine theta becomes a minus sign, and then the 1 minus e cancels the 1 minus e, so you're left with just the 1 plus e. So r equals a 1 plus e. We're also we similarly have an r1, a1, e1, and an r2, a2, e2. We're left with a times 1 minus e, 1 plus e, equals a1, 1 plus e1, plus a2, 1 plus e2. Cool? Now I add these two things together. So I just add the whole equation together. I can do that. And then the e's cancel. And I'm left with 2a equals 2a1 plus 2a2. And then the 2's cancel. One way to do this, so if anybody else has different strategies, I'm open to those strategies.
That way, but I'm wrong, so.
That's fair. Okay, so this is a satisfying proof. I like this problem. Okay, does anybody have any questions on this? This proof probably won't show up on a final or a midterm because it's just geometry, and I try to keep the final and midterm stuff to actual physics, but you should know how to do that proof because A, it's relevant for everything, and B, that kind of technique is going to show up again in your comings and goings. Okay. How am I on time? Doing okay. So given a binary system with masses m1 and m2 that are ordering their semi-major axis, find an expression for the total mass, m1 plus m2, as a function of the semi-major axis in the period. And then the second part is, given that you have the ratio q is m1 over m2, now give me an expression for both masses. So what I'm looking for here is I want a statement that says m1 equals some stuff that I know, which includes the semi-major axis and the period. And M2 equals some stuff, and Q. M2 equals some stuff that I know, including the semi-major axis. So we start off with, sorry, if I can see what I'm doing, then it makes for a better video. Can I see that? Yeah. Totally forgot what we're doing. All right. So we start with Kepler's first law. Okay, p squared equals a cubed. This is a good thing to remember, but it's not the most generic thing. This is only true for a mass of a solar mass. So that's great. That's only true for a solar mass, though, so it's not generic enough. So throw in the units, and we get 4 pi over. Is it squared? It's a 4 pi squared.
Yes.
4 pi squared over g times m1 plus m2 times a cubed. So we want an expression for m1 plus m2. We just move. M1 plus m2 equals 4 pi squared over g times a cubed over p squared. So that's the first part. Really kind of simple. But I wanted to make sure that I set you up with all the math before handing you the next problem. We had to do how to have this math done already. So you're given that Q equals M1 over M2. So then you can just say that that M2, no, sorry, let's say M1 equals Q M2. We plug into here, and we're left with M1 equals 4 pi squared over G times A cubed over P, 1 over 1 plus Q. Did we follow all that? And then for M2 equals M1 over Q, and then M2 equals 4 pi squared over G A cubed over P squared 1 over 1 plus 1 over Q. That's it. So these two things are the things that you need.
Why does it have a 1 over Q on that M2 expression?
Here. So M2 is M1 over Q.
Oh, okay.
So I drop that into here, and I've got 1 plus 1 over Q times M2. And that goes the other side. Does that make sense? And then, that's it for that problem. I'm going to leave those bits up there, because I'm going to need them in a second, like right now. So the next problem says that Sirius, the dog star, is a binary star. It's 2 stars, A and B. A is Harry Potter. With a period of 50 years, it's got a trigonometric parallax of 0.37 arc seconds. It's got a semi-major axis of the reduced mass is 7.16. The ratio of the distances. Notice I give you the ratio of the distances, not the ratio of the masses, so we've got to do a little bit there, but that's easy. The absolute bolometric magnitude of Sirius A is 1.36 and B is 8.79. So, first one is find the mass of each member of the system. I wouldn't feel bad putting this on final, so make sure you know how to do this. So, I like this problem a lot because this really goes from just what can I measure from the ground. So what do I need? I've got these two equations. What's in these equations? I've got A, I've got P, I've got Q, and that's it. So what's A? Might need to give me an expression for A because it's not in the problem.
1 over D.
Was that?
1 over D.
1 over something. You need that. So this is the semi-major axis of the orbit, right? So this is what I see. So I see these two stars, and they're on an orbit like this, around the semi-major axis. A, I don't give you. What do I give you that is going to help you get A? The parallax is important, so you need parallax. What else do I need? What'd you say?
Alpha.
Alpha. I need alpha. I need that angle, the angular size. So how do I get a physical distance from an angular size and a distance?
Alpha or D.
D times alpha.
Yeah, A is D alpha, or alpha over the parallax angle. And then this gives you the answer in AU, if you do it this way. But that's okay. You just have to not screw it up later. Is everybody good with this? So A is alpha, which I gave you, over the parallax angle, which I gave you. P, the period I gave you, is just 49. And Q, okay, I gave you the ratio of the semi-major axes. How does that relate to the ratio of the masses of A1 over, let's see, so B squared equals GM over R. I'm trying to think if this is the easiest way to do that. No, I don't like that. Let's not do it that way. Let's do it this way. Sorry, hang on a second. Oh crap! I knew how to do this when I was doing it, and now I'm forgetting. Okay, so there's a little bit of logic here that I'm just going to gloss over while the squirrels retrieve it from the deeper recesses. Q is just the mass ratio, M1 over M2, because this is proportional to the ratio of the semi-major axes of the two ellipses. So I gave you Q, I gave you P, and I gave you A, and then you just need to plug into these two formula. And that's the rest of it. Everybody good on that? All right. So 4 is straightforward once you've done 3. It's impossible if you haven't done 3. Okay, 5 and 6. I'm only going to go through one of these in detail because this is the same thing 3 times. But there's a physical interpretation that comes from all of these things, so I'm going to talk about the other results, but I'm only going to do the math on one of them. So let's talk about this first one. So helium is rare on Earth, but there's lots of it in the sun. We discovered helium in the sun, in the spectrum. Fraunhofer did that. He was like, what's this dark spot? There's got to be something there that we don't have on Earth. And he sorted that. So what we're showing here is that there isn't any ionized helium in the atmosphere of the sun. Otherwise, we would see it. So all the helium is in the ground state and neutral. So that's what we're going to show. So we're going to show that the ratio of singly ionized helium to unionized helium is something that's really small. So,
Quick question.
yeah.
Why do you use the notation that He1 is unionized? I'm struggling to understand that notation.
Okay.
I've never seen it before.
I've mentioned it, but I didn't like jump up and down on it. So now maybe I should jump up and down on it. So this is spectroscopist notation. I have some element helium, some element He, and I'm going to get it hot, and I'm going to look at the spectra that comes off of it, and I'll get different ratios of lines based on different temperatures, but I'm going to get the same set of lines as I change the temperature until I start to ionize stuff. Then I'm going to get a whole new batch of lines. Does that make sense?
So it just corresponds with different batches of lines?
Well, it does. I'm just kind of setting the stage. So I've got a bottle of helium. I change the temperature and I change the ratio of different lines until it gets to a certain temperature, and then it ionizes, and I have a whole bunch of different lines. So the first set we call helium 1. So this is unionized, and it can be excited. And then helium-2, but it's got all its electrons. Helium-2 is one electron missing. Right? Helium-4 will be 3 electrons missing. But that doesn't make any sense. So this doesn't exist. Right? Because I can only take off 2 electrons off of helium. So I can make helium-1 and helium-2 and helium-3. Helium-3 is 2 electrons missing. And then helium-4 will be another, there aren't any more. But I can make carbon-4. That's carbon with 3 electrons taken off. So this is just a notation of which element it is, and that is basically counting how many electrons have come off, kind of. It's not great notation, but it's what we're using, yeah.
What about positive ions? Is that ever a thing?
What do you mean?
Like adding electrons instead of subtracting. Is that ever a thing?
So there's H minus. Hydrogen minus is a hydrogen with an extra electron. That shows up a lot in the sun. The H minus is actually a super important ion. I don't know what you would call this in spectroscopist notation because it's very hard to get this in a lab, but it's easy to get it in the sun. So I don't actually know what that would be.
I think the main question was like, why not just call it HE and then like HE1 plus, or like HE plus, and then
That's a better
using
way to
regular
do it.
notation.
That's a
Yeah.
better way to do it, but this is what we got stuck. This is what they used. So you just got to figure this out.
Okay.
So
So just
whatever one. So if it's some element and a Roman numeral 1, that means it's got all its electrons, however many electrons it has. And then E2 is missing 1 electron, and E3 is missing 2 electrons. So if I have hot iron, so I can have iron 20, so that's going to be iron with 19 electrons taken off. Right. Yeah, sorry about that. Sometimes the notation is weird and confusing, and I forget to really pound
yeah, that
on it.
notation kind of sucks.
Oh yeah, it's terrible. Okay, so let me tell you the worst part. So when you're dealing with star formation, we have hydrogen 2, which is ionized hydrogen, and you get this around massive stars because massive stars spit out a bunch of ionizing photons. So you get these H2 regions. This is ionized hydrogen. That stuff then goes out and cools, and forms H1, and then cools some more, and forms H2 again. But I write this 2 differently, and it's a totally different thing. This is atomic hydrogen. This has 2 hydrogens. This is hydrogen with an electron missing. It's awful notation. Astronomy is filled with awful notation. Yes. Sometimes you just gotta suck it up. Is the downside of it. So you gotta know by context. So when you're in a talk of somebody who's talking about star formation, you gotta know if they're talking about an H2 region or an H2 region. Like those are either it's a 10,000 Kelvin object or it's a 10 Kelvin object.
Those
Very,
are
very
a little
different.
bit different.
Very, very different environments in
Subtle
space.
difference.
However, I'm going to treat them both as an
Little
isothermal
things.
gas, and bug it, I don't care. So it's from a fluid dynamics point of view, that doesn't care. The fluid dynamics doesn't care how many electrons there are. Okay, where am I? Saha. Did I not write down all of Saha? I'm going to screw up a mass of the hydrogen if I don't go get it.
Wait, was it not using the mass of an electron?
Was that?
Was it not using mass of an electron as mass of hydrogen or mass of a proton? Or?
I did mass of an electron because it was like
Well, it might be
subscript
mass of
E.
electron.
Yeah.
Okay.
So
I mean, I just
Yeah,
need to
it
pull
has
up the, yeah.
I mean, I've
This
always
is,
seen
this
that
is
as
one of
mass
those
an
things that I
electron.
could probably write down cold, but I would screw up a factor of 2 pi somewhere. So it's ME over KT. So it's 2 pi ME KT over H squared.
So that's rehab.
That is the electron mass. This is the part that I really don't care about as a physicist, because this is just normalization. There's not as much
all
physics in it.
constants.
So all just constants. The t is
Well,
not a
the t,
constant,
no.
but everything else is a constant. Yeah, okay, then 2 times the partition function of the upper state over the electron density and the partition function of the lower state. Let's call this, let's use notation that sucks but is consistent. So n2 over n1 is 2 over ne, z2 over z1, these are the partition functions. So this, all you need to remember about the partition function is how many particles you can cram into that energy space. And then this constant thing, and then the important thing, e to the minus chi over kt. So what this tells you is how many of the ionized things I have over the fraction of 1 fewer electrons missing. Yeah.
How are we able to have a partition function like 1.32? Like,
Wait.
but you just said it's the number of particles that can be crammed into space. So how could we have 1.32 particles crammed into space?
Ish. Think about it as ish, the number of
Just-
particles. So wave your hands, it's ish the number of particles you can cram into that state. It's, I mean, if you want the
Yeah.
proper derivation, it is the sum on gi e to the minus ei over kt. And this is just counting up how many things I have in each spot. So it's like counting the buckets, but it doesn't have to all add up to 1. This thing doesn't add up to 1 in a sensible way, and it's not quantized in a sensible way because the energy is all. So it's more like an average number. So like, you know, what's the average number of children a person has? It's like 2.5.
Yeah, 2.5.
I have 2 kids. We're gonna work on our half a kid in a second. That's so gross. So think about it as an average. Don't think about it too literally
Adopt
as a
half a
number,
kid.
but it goes like the number of particles you can cram into a space.
No more legs for you.
Just the left half kid.
Yeah.
We got the body, but not the soul.
Mm.
Oh man,
Wait, that
I'm not gonna make
should-
any. Okay, so you plug in
We
numbers.
absolutely
Here
have
you just
to.
plug in numbers, right? And then you're left with, what'd you get? Did I write down the number? I got 7 times 10 to the minus 14. Yeah.
Keep chi and EV or just
What?
keep chi and EV or just
I would do everything in EV.
okay, that's where I messed up.
Except
Yeah.
if you do,
It's the
I did everything in joules.
the knob on
Don't
whether you
think
use
I
EV or joules
converted
is which K you use.
Mm.
So if you use the wrong
Yeah.
K,
on the
then
inside, so on the inside, so that I could use electron in kilograms and H in joule seconds, I used K in joules per Kelvin. But then on the outside, I used K in EV per Kelvin, and it worked perfectly.
as long as you don't screw it up, do whatever you feel
I
like
did the
doing.
dimensional analysis because I was like, I don't want to do electron mass in not kilograms.
Yeah, you want to know how I do this, and I won't really complain if you do this. There's this really sweet Python package called Unit, and I let it take care of my units for me. So you just deal with your units. I just have a mass of a hydrogen. All of my numbers come out of that.
Can
So-
you write down the number that you got?
I got 7 times 10 to the minus 14.
Yes.
Yeah. Okay, so what does this tell us? What does this number tell us? Why do we care about this number? What is this number?
How many ionized helium there are in relation to non-ionized
It's the
helium?
fraction of ionized helium in the sun's atmosphere, and it's basically 0. This is a small number.
Game made for torture.
Oh.
Very small.
Okay, so now if we do it, we do the same thing for calcium, and I wanted to do this because I'd never done it before. I'd never sat down to work this out. But I've been talking about the 4,000 angstrom break for a long time. We'll talk about the 4,000 angstrom break in a little bit. Basically, what we see in spectra is an O star kind of looks like this, but like an A star looks like this. And there's this cliff where shorter than that, there's all of these lines, all of this crap gets absorbed from the spectrum. And this isn't because there's no light there, this is because there's stuff in the atmosphere doing a bunch of absorbing. This happens to happen at 4,000 angstroms. And it's a very useful cliff when you're looking at spectra. Yeah?
Why is it the high energy that gets absorbed, and not like the low energy, like not X-rays, radio, infrared? Why is it the high energy that gets absorbed?
That's an outstanding question. Let's think about that for a second. So, what do I have in here that's doing the absorbing? It's things like calcium that has some electrons in some energy structures. And what do we say about the cross section of this to photons that can't ionize anything?
It's low.
So for photons that can't ionize,
Zero.
it's 0. So that's why.
So it goes straight through, while like high energy, it sees all those juicy orbitals, and yeah,
Exactly.
gotta stick around.
If I've got something with 26 electron volts, then it can just ionize the crap out of all the 13 electron volts, like or it will very likely see a hydrogen and see its 13.6 electron volt bucket, ionize that photon, and then kick the atom the rest of the way. Okay, so the reason that there's this 4,000 angstrom break is because we have huge amounts of ionized calcium and ionized other stuff. It's elements that are a little bit ionized. So what we sorted out is that the number of ionized calcium atoms to the number of neutral atoms, you should have gotten a number that's like 800. So you should have gotten a really big number, because most of the stuff is ionized. And then if you look at N3 over N2, what'd you get?
0.0014.
0.0014. Which isn't 0, but it's small. Is that what I got?
Probably not.
I got 1.9, but close enough.
Yeah, that's what I got. Yeah.
Yay!
All right.
119.
How are we for time? Oh man, we are only getting through. So I do this calculus of what am I spending my time on at the beginning of the week, and I'm like, okay, I'm going to work on this here and this there, and I'm going to do this. And this morning I chose to prepare the lecture that I was going to give today that I'm not going to get to, but I didn't. Anyway, I need to talk faster is what I'm saying, so I get through everything. No, that's a lie. Mostly I'm complaining about my lack of time management skills. Because I could have gotten the homework graded and then presented, and then I would be finished with it, and that would have been so much smarter than what I did. But I do have an outstanding lecture on thermodynamics for Wednesday.
He's good at thermodynamics.
I'm great at thermodynamics. Everybody else is trash at thermodynamics. I'm the thermodynamics wizard, and so you're gonna get a grade here. Maybe I'm selling that too much. Okay, so this last problem is compute the optical depth. So, I took this awesome photograph demonstrating optical depth, but it's on my phone. I'm wondering, can I airdrop it to my phone? Bear with me 1 second. This is going to be super awesome. Bluetooth is on. Maybe this isn't going to work.
Or drop this to every single person in the class, so we can all see.
Sorry if you don't have an
My-
Android,
If
just
you don't have an Android, you can't see
My,
it.
boom. There you go.
This one? Calcium?
Okay, where did it go? Oh no, it's just out. Downloads. Okay, here you go. Okay, so one of these trees is in my backyard, and one of these trees is in my immediate next to me's neighbor's backyard. So this tree is really not very far away. I mean, it's just like behind this tree. But this tree is, in my yard. So what's the difference between this tree and this one?
The mist.
Atmospheric diffusion.
The beast.
The
fog,
mist.
The mist. So I have a whole bunch of stuff in between me and this tree. So what we're going to do is compute how much stuff. Now I can't actually compute the distance, and I can't compute the mass of stuff, but I can compute the product of the distance and the mass of the stuff. So I can compute the optical depth, tau, which is rho times kappa times L, the length of the cloud. make sense? So this is what we're going to compute. So let's do that. So we want to compute. We're not going to do it for this thing. But I was actually upside down looking out my window, and this beautiful image of column density appeared. So we're going to compute how much stuff is in the way. Where's my thing? Get rid of you. I just close you. Why are you still open? All these things that were open last. Okay. Oh, I only have 3 minutes left. We got to do it. Okay, so what's the question say? Every A0 star. So I like this problem because I don't know, it connects a bunch of things. Every A star has a magnitude of absolute visual magnitude of 1.1. This just comes from sigma t to the fourth, right? This is just the temperature of the star gives you a black body, and it gives you this certain visual magnitude, right? So if the star is located at 400 parsecs, let's get the apparent visual magnitude. And then what we're going to do is say, okay, we didn't actually get that visual magnitude. We got something that's bigger, so the thing is dimmer. So let's compute how much crap is in the way. And then we'll do it again for the infrared. And we'll show that there's less stuff in the infrared than there is in the optical. Does that make sense? So, MV is minus 2.5 times log base 10 of the luminosity over the luminosity of a zero magnitude star, the fiducial luminosity. So if this star were actually at 10 parsecs, but there was a cloud in the way, we would get MV prime equals minus 2.5 log base 10 of L times e to the minus tau over L naught. Because then I've got tau's worth of stuff in the way. And I can simplify this. This just turns into minus 2.5 times the log base 10 of L over L naught minus 2.5 times the log base 10 of e to the minus tau. Right? So I can do this log, and I'm just left with this is equal to MV plus 1.09 times tau. Okay, does everybody see how all this math works? How I got to this point? Why I got to this point? So then the apparent brightness, so the first problem, so I kind of jumped the gun a little bit. So the apparent brightness is just MV plus 5 log 10 of D over 10 parsecs. So I gave you this, and you plug in for this. What did you get for the 9.1? So you should get 9.1. And I said call this V, because this is the visual extinction, so we're going to call this V. I'm going to call this V ideal. This is 9.1. So then we need to compute what the column density is. So we have V observed minus V ideal is going to be, well, V observed is just going to be this part. V ideal is going to add on this. So the difference of this is just going to be minus 1.09 times tau. So tau is equal to 2.9, which is optically thick. Anything bigger than 1 is optically thick. I did that kind of fast, but I'm running out of time. So the second bit,
What if tau equals 1?
was that?
What if tau equals 1?
That's optically thick.
That's thick, okay.
Yeah. So if tau equals 1 or more, that's thick. So then the second question says do the same thing for the infrared, and I said, okay, it's got a V minus K color of 0, so K ideal is going to be also 9.1. And see, let's see, I gave you the observed K, right? So the observed K is 9.8. So we're going to have a similar equation like this. K observed minus K ideal is going to be 1.09 times tau in the K we just do a little math, and we get tau in the k equals, what do I get, 0.6. So this one is 2. Remember what tau does. Tau is e to the minus tau. So if tau is 2, then this quantity is like a quarter. It's like 1 over 2 squared, right? But if it's 0.6, then it's like 1 over the square root of 2. So it's a lot smaller. Wait, that is it for today?
So what does V minus K mean?
Is that V minus K is a color.
Okay.
So those are two. So V is the brightness in V and K is the brightness in K. So that's just an infrared band. So V minus K is just that color.
Okay. So we're supposed to use the observed or the observed magnitude that we already had in the previous problem. Because I was just looking at 0, so I did 9.8 minus 0 over 1.9.
Yeah, this is 9.8. And then that's 0, so K's got to be 9.8.
Oh. Okay.
Yeah, that makes sense.
That's